Okay. Okay, so this is session number 7 in computing fundamentals. And so this session is about multiplication of matrices and also polynomial evaluation. So there are 2 topics here in this session, and remember that sessions from 1 to 7 are included in the exam, right? In the midterm exam that is scheduled for the 28th of April, correct? Yes? So you have it there in your plan, right? So the idea today is to review, the conventional algorithm for matrix multiplication, but also other 2 algorithms. And also we will discuss the lower bound of multiplying 2 matrices, right? And then we're going to talk about how we can evaluate polynomials, right? Even the polynomials and some values there. Okay, so let me share the screen. Okay, so you should see my presentation there.
Yes.
Okay, 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 good. So this is session number 7, right? So matrix multiplication on one side and then polynomial evaluation on the other. So remember the topics on the previous sessions, the session number 6. What was that session about? Hmm? Is it true that after a presentation, after 7 days of a presentation, the students only remember about 10% of what you did in that presentation? Is that true? Do you remember the 10% of that session? What was that session about? Remember last week? Someone?
About binary search.
Mm-hmm. What else? In general, the topic was about what?
Selection.
Selection problems, right? What else did we do? Binary search, the analysis on the worst case, the analysis on the average case, and then what are the initial problems in selection? Finding the what?
The max and the min.
Maximum and minimum, and second maximum. And we discussed a little bit the adversary argument, remember, for the maximum and minimum. What else? What was the last part of that lecture in particular? Was about the algorithm, the linear algorithm for finding the k, right, largest. Remember? Was a little bit tricky. So what I'm going to do this Friday in the morning, I'm going to open a kind of review tutoring session, right, for the 3 last sessions, and also review the homeworks that you have, previous to the exam, 5, 6, and 7. And hopefully this week also we will have the feedback of the first 4 homeworks that you submitted a few days ago. So I will upload an announcement about this session on Friday morning, okay? So today, So we'll see matrix multiplication, the lower bound, and two algorithms for doing that, right? And then we go to 2 or 3 algorithms for evaluating polynomials, okay? So ready to go. Okay, let us start. Let us suppose I have two vectors, V and W, right? And each has n elements, n numbers, right? V is V1 to Vn, and W is W1 to Wn. And what is the meaning of the dot product of two vectors? How do you define it? How do you define the dot product of two vectors? V1 times W1, right? What else? V2 times W2, and so on, right? Vn times Wn. And what do you get? What is the result of this expression? What do you get?
That is a projection of the vector in the other one, right? Like the distance of the projection.
And what do you get? What do
A
you
number,
get?
a scalar number.
A scalar number. That is important, right? So you get this scalar, this number. It's what you get out of this dot product, right? Now, if I want to count the multiplications and the sums of this operation, what is the number of multiplications? N, correct. And what is the number of sums?
N as well.
N. What else? N. What else? -1, right? Because I have the summation of n numbers, so I'm going to spend n-1 sums for doing that. Is that correct? Is that clear?
Yes, it's clear.
All right, good. So this is the basic of the matrix multiplication, as we will see in a second. Okay, so but this is important. This is the dot product, and then this is the number of multiplications we use, and this is the number of sums that we use for doing that. Okay, good. Let us continue here. Let us suppose now that I have a matrix, right, of size n times n, and I want to multiply by a vector size n, right? What is n in matrix A? What is n? What is n? Can someone tell me? This is a matrix, size n times n. So what is n?
The number of rows.
Number of rows, that is correct. And what is n?
The number of columns.
Number of columns, right? And this is just one column, right? And what is the resulting structure that I have after multiplying this matrix by this array? What do
It
you
will
do?
be a row vector of 1 by m. M by 1, sorry. No, what?
Size
Yeah, a
n,
1 column vector.
right? And what do you get here in the first cell of this array? What do you do?
the dot product of the first
The
row
dot
of
product of which?
the first row of A
The
by
first row by
the column of
the
the other one.
column that I have. So I do the dot product, the same operation we did in the previous slide, and I get the scalar number here. That is the first element of the resulting vector, right? So how do I get the second element in M? Second row here with the same column here. I get the dot product of that, right? And so on. So I get the mth row dot product with this column, and I get the last element here, right? So that is the resulting vector here of size n, right? Now, in this operation, in the whole operation here, what is the number of multiplications that we use? For this, the first one, what is the number of multiplications that I use? This is of size n, right? And this is of size n. Number of multiplications for that. For the dot product of the first row and the column and the vector here. What is the cost? What is the number of multiplications for this and this? Same as before, right? N. But I have how many rows to compute? N, right? So the cost is going to be n times n. Are you following me okay?
Yes.
Okay. So do you agree that the number of multiplications for this is this number here? Okay. And now the number of sums. So how many rows? M, right? And how many sums for each row? How many? How many?
N minus 1.
N minus 1, right? The same as, in the previous slide, we used it for just one row, right? One dot product, I'm sorry, but now I'm using for M rows, and for each I'm going to spend N minus 1, right? So in general terms, if M is equal to N, this is like N squared, right? And this is like N squared minus N, right? If M is equal to N, correct? So are we doing okay? So far, so good,
Yes.
right? Okay, good. Now, let's go to the general case, right? The matrix multiplications, and in which I have two matrices, right? One is M times N, and I'm going to multiply by another matrix, which dimension are N times Q, right? So what do I do in this matrix multiplication? What should I do? How do I get, for example, the first element in the resulting matrix? What is the size of the resulting matrix, the matrix C here? So if this is A and this is B and the resulting matrix is C, what is the size of this matrix that I get at the end?
M by Q.
M by Q, correct, right? N rows, Q columns, right? So I want to compute this element, the first, which is C11. What should I do? Remember? What should I do to get this first element here in C11? Remember, it's what?
It would be the first
First row and
by the first column.
first column, the dot product of those vectors, right? How do I get the second element in the first row of C?
The second row by the
first row here.
Yes, the first row by the
second column here, right? So this is the element here. So the first row by all the columns here is the first element, right, in the first row C. How do I get the second element in the first column of C? It's what? Second row, first column, right? Second row, second column is this one, and so on. Did you get it? Did you get it? Yes or no?
Yes.
Okay, so for each element in C, I need to do a dot product, right, of a row in A and a column in B. Correct. Now, let us count the number of multiplications, right, and the number of sums. So for each element here is going to change color again. So I have M times Q elements in C, right? Here. For each element, how many multiplications do I need? The size of this row is n, and the size of this column is n, right? That's the reason these two dimensions in each of the matrices match, right? So what is the number of multiplications here? N times Q, which is the number of elements in C, and for each I'm going to spend how many multiplications? How many?
N.
N, right, correct. N times Q times N. So this is the total number of multiplications we are using in this algorithm to compute C, right? And for the number of sums, I have this number of elements in C. How many multiplications? How many sums? I'm sorry, how many sums?
N minus 1.
N minus 1. All right. Now, consider that the dimensions are n times n, and this one is n times n, and this is the resulting matrix is going to be n times n too. So if this happens, right, this is going to be what? N is going to be NQ, right? NQ multiplications to get, right, the result matrix here. How many sums? N Q minus N squared, right? So this is the complexity of the conventional algorithm for multiplying two matrices. Do you agree with that? So the complexity of this, the number of multiplications is n cubed, and the number of sums is n cubed minus n square. Is that okay? What do you think? Hmm?
Yeah.
Clear so far?
Yes.
Is
Yes.
that understood? So we came from, from the dot product of two vectors, from a matrix to multiplied by a vector, and now two matrices, right? And the resulting matrix, right, with these dimensions and the complexity of the algorithm, right, using the dot product there. So this is n cubed, and this is n cubed minus n squared, which, actually the complexity is what? N cubed, right? Because the largest term is this n cubed. So we're doing okay then up to now. So that's the first algorithm for multiplying two matrices, right? So I'm going to move on and present to you two additional algorithms for doing matrix multiplication. I don't know, probably this one, you have used this one, for different purposes, but this is the conventional algorithm for multiplying two matrices, right? Which is somehow easy, right? How many loops do you have in this algorithm?
3.
3. The one is going from I to M. The second one is going from 1 to Q, right? And the third one is going from 1 to N. And if you know all the dimensions are the same, let us say N, so you have 3 loops from 1 to N, right? That's the reason you have this number of multiplication. Clear? Okay, let us go on. Now, the second algorithm is called the Winograd's algorithm for multiplying two matrices, right? And what this algorithm is going to do is the following. Let us suppose you have the two vectors here of size n, right? And let us suppose that you have 4 elements, n is equal to 4. So what you're going to do is the following, right? To get the dot product, you sum up B1 and W2 and multiply it by B2 and W1. You see? It's like you get the first element here, and then you sum it up with the second one, right? And then you get the second one here, and then you sum it up with the first one of the row. And then you continue the third with this, and the fourth with this, and so on, right? You see? You are summing up pairs, one element in V and one element in W, right? And then you're going to, all the elements in B multiplied by pairs, B1 and B2, B3 and B4, B5 and B6, and so on, right? And then W, also W1, W2, W3, and W4, and so on. So do you understand the dot product of two vectors using Winograd algorithm? Is that okay? And you can check it out if what you get is the same as the previous algorithm for getting the dot product, right? You should get the same, which is a scalar number, right? It's a different way of doing that. Okay? We're going to count this at when we have the two matrices, right? So do you understand this? The dot product using the Winograd algorithm. Do you understand what the algorithm is doing? Right?
Yes, doctor.
Okay, good. Let us go. Now, The last four multiplication involved, so this is an observation in which the multiplications at the end here, right? For this case in particular, when n is equal to 4, this is only involving elements in V, and these are only involving elements in W, right? Only two multiplications involve components of both vectors. Just in this case, these two multiplications involve elements in the two vectors, right? The formula relies on the commutatively of multiplication, right? But for the numbers, right? This is, the commutativity property doesn't apply when we have matrices. In here, we have elements. That is okay, right? Now, let us consider the general case. So I need your attention here, right? I need your attention here. Let us say that n is equal to 2p, right? So the idea is that n is even. That's the idea, the main idea, right? And this is the general case to get the dot product of two vectors with size n and n is equal to 2p, right? So what I'm going to do is to sum up the pairs, right? When I is equal to 1, this is 1 and this is 2, right? When I is equal to 1, this is 2 and this is 1, right? Is that okay? And these two elements are multiplied, right? So I'm going to do these steps here, right? And get all these multiplications, and then this, summing up first and then the multiplication of those two elements, right? And then I'm going to get here the pairs, right? B1 and B2, B3 and B4, etc. And I'm going to subtract, right, from this expression, and I'm going to get P elements, right? P pairs, I would say. And the same for W. So W1 and W2, W3 and W4 time. So this is the general, right? The general expression for getting the dot product VW, right? And if n is odd, well, P is equal to n over 2 floor and add the final 10, this, right, to equation 1. This is what you're going to do. So up to now, do you understand this expression here? So this is for the dot product of two vectors of size n using the Winograd algorithm. Good so far? Easy, right? Yes? Okay. Let us continue then. Now, okay, let us suppose I have a matrix m times n and another matrix called n times q, right? Same thing. I'm going to get here the C matrix of size m times q, right? And the first element here is going to be computed using the Winograd algorithm, right, for getting the dot product, right? So what I'm going to do, right, is to get the alpha I for each element in A, each row, I'm sorry, in A, I'm going to get all the alphas, right? For example, here I have A, which is m times n, and this is m times q, right? And for this row, right, I'm going to get this. That is B1, first element times second element, third and fourth, 5 and 6, and so on, right? P pairs there, right? You see, for each row I get the multiplication, the pairs. And this, I'm going to keep them in an array called alpha I. How many I's do I have? Number of rows, right? Which is n. Do you understand this? So for each of the rows, I'm going to compute alphas, the alpha I, right? So do you understand this expression here? Tell me, please. Yes? So again, do you know what this expression is doing? Yes or not? Yes or not? And then
It was not, sorry, it was not so clear to me.
Not clear. Okay. So I'm going to return, right, to the previous expression here. Remember, here I have the summation of the elements B1 and B2 and B2 and B1, right, and multiply. But here in the expression it says you consider pairs in the same vector, right, and multiply B1 and B2, B3 and B4, right, B5 and B6. Here for this row in particular, for this element, in this case it's for B, right? And the same for W, W1, W2, W3, W4, and so on, right? So now, in the general case, these are the alphas and these are the betas. But for each row that I have in the matrices, right? For each of these rows, I'm going to compute 1 and 2, 3 and 4, 5 and 6, and so on. So this is the expression here. The alpha I for each I, which is the row, the ith row, I compute that, right? The first one and the second one, the third one and the fourth one, and fifth and sixth for the row I, right? So this is like the alphas, right? For each row in A, right? And for each column in B, I'm going to do the same, right? B1 and B2, B3 and B4, B5 and B6 in the ith column. And the column is going from 1 to Q. Is that clear? So these are the betas, right? For each column. Now, since I'm using just elements in the same row or column, this I can pre-process these elements, right? So I have all the alphas at the beginning, I have all the betas at the beginning. Now, if I want to compute each of the elements in C, right, what do I need? One row in A and one column in J, right? So this is, I'm going to compute the IJ cell in C. So I'm going to use this row and this column, and I'm going to use the same expression that I did for the winograd, right? First element in the row, second element in the column, times second element in the row and first element in the column. You see? And then you subtract the alpha I that you have already, and you subtract the bj that you have already. So does this expression make sense to you? So I'm computing with this formula all the cells in C, right? How many cells in C? M times Q. Up to now. Is that okay? Is that too fast? Please tell me if you don't clearly understand what I'm doing.
I think it's okay.
Yeah. So just consider that I'm computing the dot product of the ith row and the jth column, right? But I need to do that for each of the cells in C, right? How many? N times Q. So this is the expression that I need, the row I, the column J, and the elements, right? The first one and second one and third one. Third and four and three, right? And subtract alpha, the corresponding alpha I or beta J, right? So I'm computing here each element of C, okay? So do you understand the algorithm, right? Because
Yes.
next we are going to do, we are going to compute the complexity for this algorithm, for the whole algorithms in order to get this matrix C, right? Now, okay, let us go and do that. This is the analysis of the algorithm, right? Let us assume that N is even, right? So N is equal to 2P. P is equal to N over 2. We're going to use it later, right? Number of multiplications here. Processing rows of A, right? How many rows in A? So this is for computing the alphas, basically. What is the cost for computing the alphas for each row of M? Of A? How many? M, right? And I'm computing for each row pairs, right? How many pairs? P,
P.
right? So does this number MP make sense to you?
Yes.
Right? This is for A, and for each row in A, I compute by pairs, right? And I have P pairs, so, and I have M rows, so I'm going to spend N times P multiplications, right? For the alphas. Now, what else? Processing, these are the alphas and these are the betas, processing columns of B, right? This is N times Q. So for each column, I compute the pairs, right? 1 and 2, 3 and 4, etc. How many pairs? P. And how many columns?
Q.
Q, right? So I spend NP here and QP here, right? So I'm counting only multiplications so far, okay? So these are the betas, right? These are the betas, right? And let us continue. Computing the entries in C, right? How many entries in C do I have? M times N. This is N times Q. And the resulting is M times Q, right? For each position in C, right? How many multiplications? M times Q, that is okay, right? And for
Yes.
each position here, how many multiplications? Remember, I'm going to go back a little bit, okay? Just to show you why should be P, right? This is going from 1 to P and is multiplying pairs, right? So I'm doing for each element in C here, I'm doing P multiplications. You see? So that's the reason I have M times Q, right? Number of cells in C times P. Is that correct?
Yes.
Okay. So we have MP, QP, and QP. The total of, total number of multiplications that the algorithm is doing, right? If P is equal to N over 2, so I'm going to have here a N times N over 2 plus, this is N times N over 2 plus, this is what? N times N times N over 2, right? In total, this is going to be what? This is N cubed over 2, which is this, right? And this plus this is what? N squared. You see? This plus this is N squared plus N cubed over 2, right? So this is the total number of multiplications, right? That are used in the winograph, right? This number. Is that okay?
Yes.
How is this compared to the conventional algorithm in the number of multiplications?
Similar, but the half is smaller.
No, this is greater, right? Because in the, well, okay. Yeah, it's true. This might be half of N squared, but there's some addition here. More or less in general terms, it's an N cube, right?
Yes.
Okay. But it's a different way of doing matrix multiplication, right? I don't know what Winograd was thinking when he designed this algorithm, but that's the same, right? Now, yes,
Sorry,
questions?
to me it's confusing. So why we have the dot product?
Why do we have the dot product?
If you go back
Uh-huh.
when we sum the alphas and the betas, I mean I get what they mean, but why do we consider them?
Well, it's because it's like you consider multiplications, but it doesn't mean that you have the result here. So you need to subtract some number there, right, to this total that you get here. So you need to subtract these two numbers in order to get what you get, what you have, or what you need, the dot product. Wow, it's the design of the algorithm.
Yeah, okay.
Seems that this part is going to contain more elements or a value that is greater than the one that you need. So you subtract this element. All right, but at the end, what you get is the dot product, right, of the two vectors. Same as in the conventional algorithm, but except that the number of multiplication is going to change a little bit. Right? Now, if I want to count the number of sums, right? by processing the alphas, what is the number of sums that I do? Well, remember the alphas here again. Alpha is, I have multiplications, P multiplications, but I have how many elements here in this summation? How many elements?
P.
P, and yeah, I want to sum them up. So how many sums there?
P minus 1.
P minus 1, right? For all the n rows that I have. So that's the reason, right? I have a number of sums that I have for that case. For the alphas is m, right? Number of rows, and P minus 1, right? The sum of P terms, right? So the same is going to be for B, in which you have Q columns, and for each column, you're going to sum up P terms, and it's going to take P minus 1 sum. Is that okay? So this is alphas, and this is for betas, right? Is that okay? So these are for alphas and betas, but what about for the product? Computing the all entries in C. How many cells or how many entries in C?
M times Q.
N times Q. Now, let us see the number of sums, right? I'm going to go back again just to get this number, 3P plus 1. Let us think about that. I'm going to erase this. Because I need to count all the sums here for each cell, right? So I'm going to count for each cell here the number of sums. I have one here and one here, right? And I have a sum from 1 to P. How many sums in that expression? How many?
P minus 1.
Is P 2P, right? 2P, right? Indeed, because I have 1 and 2 in P times, right? So this is 2P. Do you agree?
I don't understand why 2P.
Because I have 1 here and 1 here, right? And I multiply this number here and this number here, right? After I sum up here, 1 and 2. In how many times? P times.
Does the minus alpha minus beta count
Oh,
as a
I'm not counting that
Okay.
yet.
Right.
I'm just counting this, right? This, and I have P terms. So this is 2P. Plus, I have P terms, and I need to sum them up. So how many sums? How many sums according to this summation here?
P minus 1.
P minus 1 plus 1 and 2, right? Alpha and beta is just one element here, and I subtract it, and one element here, and I subtract it, right? So there are 2 sums there. So what is the total number here that I have? 2P plus P minus 1 plus 2. How much is that?
3P plus 1.
3P plus 1, which is the number that I have here for each entry in C. You see? Clear? So what is,
Sorry, Professor, the
yes,
P minus 1 plus 2. Can you explain again?
yes,
How
I'm going back. Okay,
do we-
yes,
oh,
of
thank you.
course. So let me repeat. Okay, I'm going to raise again, no problem. Right, I have this expression for each entry in C. You see? So I have this one and these two, right? For each of these P elements. So that is going to take 2P. Do you agree with that?
Yes,
1 and 2 in P times, right? But this summation, how many elements has?
P.
P elements.
minus
If I
1.
want to sum P elements, how many sums do I need?
P minus 1.
P minus 1, which is this, right? And then I have these two subtraction considered as sums, and I just add 2 here. So I have 2P plus P minus 1 plus 2 in total, right? For each position in C. So that is 3P plus 1. Is that clear? Is that clear?
Yes.
Okay. All right. So let me move forward. Okay. So I have this for alphas and betas, and this is the total. So if all the dimensions are the same, equal to Q equal to N. So this is going to be, the total is going to be, and in P is equal to N over 2. So I have N times N over 2 minus 1. So this is this, and this is N over 2 minus 1, right? And this is N squared times 3 N over 2 plus 1, right? So this is going to be 3 halves N cubed, which is this part, right? And then I sum N over N squared over 2, N squared over 2, which is plus this, N squared over 2, which is N squared, and this times this is going to be 2N squared, and this is minus 2N, right? So this is the total number of sums here, which is a little bit more than the conventional algorithm, right? So this is, at the end, this is N cubed, and this is N cubed also. Same as the conventional algorithm, more or less, right? So this is the complexity of this algorithm in particular. So is that clear so far? It is a little bit tricky, but not too much. I know that is important to understand that I have a matrix n times n, and I have another matrix which is n times q. I'm going to get a matrix n times q. And for each one, I'm just computing the dot product using this algorithm, right? And this is the total number of multiplication, and this is the total number of sums, right? So, questions so far? questions so far?
No, everything is fine.
That is okay. 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 So, well, this is the first algorithm, apart from the conventional algorithm for doing matrix multiplication. Now, let us check the other algorithm. The other algorithm is called the Strasson's algorithm, right? And the Strasson's algorithm considers the following, right? I have a matrix A of size 2 times 2 and a matrix B of size 2 times 2. So before we proceed, if you do the multiplication A times B, what is the resulting matrix C here? What is this first element? How do you get the first element in C using the conventional algorithm? A11, A12 with B11, B21, right? So you have this multiplied by this plus this multiplied by this, right? And you get this element, right? How do you get this element here? This row and this column. This element here, this row, this column, and this element, this row, and this column. Tell me the number of multiplications that you use for finding C with the conventional algorithm. How many multiplications? Number of
Okay.
multiplication.
8.
Yeah, 2, right? 2, 2, and 2, right? So 8 multiplication. Number of sums. How many? N squared minus n cubed minus n squared. Remember? Number of sums. 8 minus 4,
2. 2.
4, right? 8 minus 4,
Yes, 4.
right? Which is 4, right? This is using the conventional algorithm. Now, let us observe. We know that, if you multiply this matrix and this one, it's going to do the following. It's going to get all these 7 numbers here by summing up A11 and A22, A11 and A22, multiply by B11, B22, B11, B22, and then multiply, right? And then X2 is A21, A22 times B11, and so on. So it's going to get all these 7 numbers, right? So you don't have to memorize all these numbers. So what you need to understand is that it's doing this number of multiplications, right? 1, 2, 3, 4, 5, 6, 7, right? And then in order to get the elements in C, right, it's going to sum up the elements in X, right? And you're going to get the result here. Now, for this size of the matrices A and B, count the number of multiplications in the Strassen algorithm. How many?
7.
1, 2, 3, 4, 5, 6, 7, and I don't have any more multiplications here, right? 7, And I count a number of sums also. So 1, 2, 3, 4, 5, 6, 7, 8, right? 9, 10, 11, 12, 13, 14, 16, 17. No, should be 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. Number of multiplication is 7. Number of sum is 18. Well, is that efficient or not? For this case,
No,
it is
too
not.
many sums.
Too many sums, and one multiplication less. Does that compensate that reduction of multiplication with respect to the number, to the increase in the number of sums? Well, probably not, right? For this case in particular, but let's check the general case in which I have the two matrix, n times n and n times q. And how do we define the multiplication of a Strassen? So I'm going to use, n, and I'm going to say that n is, this is n times n, and this is n times n. And let us suppose that n is a power of 2. So I'm talking about sizes of the matrices like 16, 32, 64, etc., etc. Why is that? Because I can, divide up the matrices, and the size of this matrix is going to be what? N over 2 over n over 2. This is n over 2 times n over 2, n over 2 times n over 2, and this is n over 2 times n over 2, and so on, right? So this is A11, this is A12, this is A21, this is A22. So the algorithm, the Strassen's algorithm, is going to work as divide and conquer, right? And you can imagine, right, what the algorithm is going to do. So it's going to, if I have a matrix n times n, what is the size of this matrix? A11.
1, 1.
No, if this one is n times n, right, I have what, 4 submatrices, each one of size what? As I was,
1.
n over 2
N over
over
2.
n over 2, right? The size of this matrix is n over 2 times n over 2. Same for this one, same for this one, same for this one. Right? Are you following me or not?
Yes.
No? You are? It's like this, right? I have a matrix now, n times n, multiplied by another matrix n times n, but I'm going to divide up this matrix A into 4 submatrices, right? And this B into 4 submatrices. Each one is going to be size n times 2 over times n over 2 times n over 2. Each of these. This is A11, this is A12, this is A21, this is A22. So I'm going to apply the algorithm right? And this A11 is going to be what? The matrix here of size n over 2 times n over 2. A22 is going to be this one of size n over 2 times n over 2. B11 is this one, but now it's a submatrix, right, of size n over 2 times n over 2. Same here, same here, same here. So I'm going to do all these operations with matrices of size n over 2 times n over 2, right? So I received a matrix multiplication of size n times n, right? And I'm using submatrices of size n over 2 times n over 2. When I multiply the resulting matrix of here, A11 plus A22, what is the result of this matrix? The summation of two submatrices. What is the result? A11 plus A22. This is a submatrix of size n over 2 times n over 2. This is a submatrix of size n over 2 times n over 2. When I do the sum of these two matrices, what do I get? What do you do in a sum? So you sum this element plus this element, and you get this one, the second, and you get this one, and so on, right? So that's the summation. You are going to get a matrix of size n times 2 times n times 2. Do you agree that this part is going to be a matrix n over 2 times n over 2? And what is the result of this sum?
Another matrix n over 2 and over 2.
That's correct. And then now you are going to multiply here, right, the two submatrices. Using what? Winograd algorithm. So this is a recursive algorithm, right? So for this multiplication here, you're going to generate the 7 operations here again, but with matrices of size what? Just for this.
N over 2.
N
Times
over
n
2
over
over 2. So
Ah.
N over 2 over 2, right? So the operations, the 7 operations here are going to consider now matrices of size n over 2 squared, and so on. So that's the reason this is a recursive algorithm. Is that clear? And I
Yes.
have to do that, you know, the 7 multiplications now with n over 2 times n over 2 operations. And for each one, I'm going to do 7 operations, and the other part, you know, in the next slide here, for each multiplication of matrices of size n over 2 times n over 2, but now the operations are with with matrices of size n over 4 or n over 2 squared, and so on. The next step is going to be n over 2 cubed, right? And what is the stopping condition here in the recursion?
2 to the k.
2, right? So when you have matrices of size 2, so you're going to stop there, right? And the recursion is, you know, coming up, right? So do you understand that this algorithm is divide and conquer,
Yes.
right? Now, let us consider the number of additions for this algorithm, right? Number of additions only, right? So you have matrices of size n times n, and you have 7, right, multiplications there, and you need to count the number of summations there for matrices of size what? N over 2, n over 2 times n over 2, right? And where this 18n/2 square is coming from.
The summations, right? We had 18 sums.
18 sums, and each of the sums is considering matrices of size n/2 times n/2, right? So I need to get n/2 times n/2 elements in the matrix. So this is going to be this number of operations time 18 because I have 18 sums, right? So this is 18 and this is n/2 times n/2, right? And this is 18 times because I have 18 sums and I have 7 multiplications of size n/2 times n/2, but I need to go and count the number of sums there. So if you manipulate this expression, you can use, either the substitution or you can use the master theorem, you are going to get this expression. And how this expression compares to the number of sums that we did for conventional algorithm or the Winograd algorithm.
It's smaller, right?
It's smaller, right? Because for those, it was n to the cube. And this is actually reducing in the exponent, right? So actually this complexity is much better than this one in the number of additions here, right? Now, what is the complexity in the number of sums, in the number of multiplications? I'm sorry. I only have 7 subproblems of size n/2 times n/2, right? And I don't have any more multiplications in the other operations that the algorithm is using. So this is an expression, right, for computing the number of multiplications, which is a recurrence, right? If you solve it, you are getting this complexity. What is this complexity compared against the other algorithms, which are in cube? This is much better, right? Because the exponent is smaller than this one, right? So for the general case, right, the complexity on the number of sums and the number of multiplication is much better than the 2 algorithms that we previously reviewed, right? Because now we are talking about a decrease, an important decrease in the exponent of the expression, right? And this is much better than this. So, what do you think? What do you think? What are the disadvantages? Here in the Strassen algorithm, we are using divide and conquer algorithm, right? What is the possible disadvantage of a Strassen algorithm? It is good in the complexity. What is the possible disadvantage? Because the other one in the conventional algorithm is just iterative, right? I have the loops and then I compute, the each element in C. And in this one, what do you think is a possible disadvantage of this algorithm?
That you are assuming that n is equal to 2 to the k, so you don't have any other dimensions of that.
Well, you may, right? And a possible disadvantage is that possibly you need to fill out with zeros, right? And probably you spend a lot of space there. But also remember that recursion is going to keep your matrices somehow in memory, right? Because it's going to solve recursively, right, the multiplication of the matrices. Right, so you're doing recursive one phase, and then you keep the matrices somehow. And if the matrices are large enough, you're going to spend a lot of space. Is that clear or not? Make sense?
Yes, Professor.
Mhm. But, you know, the complexity is better. It's better. And there's literature, there's a, I think, modified extraction algorithm in the literature that is a little bit better than this one. But this is the basic algorithm, and you should understand this one, right? Okay, so let us talk before we go for a break about the lower bound for matrix multiplication. So we have, you know, well, we have a little bit, this is the lower bound. So I have the algorithm conventionally, which is n to the cube, and possibly Winograd is about here. And then I have the other, which is the Strassen algorithm, which is n to the 281, right? The question is that if is this algorithm optimal? And the truth is that it's not, right? There's no optimal algorithm for matrix multiplication. And what is the lower bound? The lower bound, the best known lower bound is surprising below, m times r, which is n squared. M times n multiplications are necessary to multiply n times n matrix by an n vector, right? Remember? M times n by an n vector, this is going to take n squared, n times n, right? Or n squared. So the lower bound for my multiplying two matrices is n squared. Now, you can do two things here, you know, when you don't have an optimal algorithm. One is to formally move the lower bound to the right here, or keep improving the algorithm, right? And then try to just match the lower bound and the complexity of the algorithm in order to say this is the lower bound and this is an optimal algorithm for doing that. But currently, you know, I think the best algorithm is around here, and this is still, you know, the lower bound. So conclusion is that we don't have an optimal algorithm for multiplying two matrices, right? Because the lower bound is n squared, and the best algorithm for multiplying two matrices is like n to the 259 or something like that, right? So people are trying to find better algorithms for doing that, and this, well, it's not, no one has formally presented, you know, that the lower bound is greater than this, right? So this is one of the cases in which we don't have an optimal algorithm for solving the problem, right? The algorithms are good, right? But not necessarily optimal, right, for this problem in particular. Is that clear? Because for all the other problems that we solved in the past, we had, you know, the lower bound, and we had at least one algorithm for doing that, right? For an optimal algorithm, right? For doing that number of operations, not for the case of matrix multiplication, right? Is that okay? How are we doing? How are we doing? Okay? I
Okay.
think we need to take a break. I'm going to stop here the recording and then we come back. Okay, second part of the session is about evaluation of polynomials. And let us define first what a polynomial is. It's an expression, right, p of x, in which x is a variable that is given, right, and have this an, which is a coefficient, times x to the n, an minus 1, which is another coefficient, times x to the n minus 1, and so on, a1 times x, and a0, right? So we have all the ai's, right, from 0 to n, and then x, which is kind of variable that is given, right? And what is the value of p of x? Well, it's just obtained, right? For example, algorithm 1, which is an iterative algorithm, is going to take, you know, a0 plus a1x, so the first part of the polynomial from here, right? This part, and then it's going to continue computing all the elements, right? Iteratively from 2 to n, right? X power is equal to x power plus x, right? And then you add the following coefficient, and then you sum it up, and then you continue here up to n elements in the polynomial, right? So this is, right, very easy algorithm, very conventional, and in which you, you know, if you do the analysis of the algorithm, what is the number of multiplication that the algorithm is doing here? So you have one multiplication here, right? What else? How many times this cycle is n minus 2 plus 1, which is n minus 1, right? Here. And this is 1 multiplication, and this is 2. So 1 plus 2 n minus 1 multiplications, right? And sums, this is number of moles, which at the end is 1 plus 2n minus 2, which is 2n minus 1, right? Which is linear. Number of sums is equal 1 here, and then 1 here. So it's going to be 1 plus n minus 1, so it's going to be n sums, right? In total. Okay, so both are linear, so they are easy algorithms, right, for doing this. The algorithm number 2 is, you know, works in a backward way, in which, you know, you decompose the polynomial in this way: a3 times x plus a2 times x plus a1 times x plus a2, right? And you get the result also. So what you're going to do is, like, you know, for the general case, is this is the algorithm number 2. So you start in the n element, and then you go from n minus 1 down to 0, right? And you get the expression, right? P times x, right? plus AI, and then you continue in the cycle here. So the number of multiplications here is what? Is here 1 times n minus 1 to 0 is going to be n. Multiplications and number of sums is 1 also. So it's going to be n also. So they are linear, a little bit more efficient than the previous one, but at the end is, you know, linear for both cases, right? So this is algorithm number 2. Okay, so and algorithm number 3 is an algorithm based on divide and conquer, and it has specific conditions, like, you know, you have n is equal to 2k minus 1. So you have, for example, if k is equal to 4, you are going to have n is equal to 15, right? And also, the other assumption is that a of n is equal to 1. So that is called a monic polynomial. So this element is 1. If you don't have it, just divide up by a of n, and then you have the polynomial, and at the end you multiply it by a of n, right? And you get the result. So, okay, so let us do what this algorithm does, right? Assume that n is greater than 1 there. Is written in the following form for some j and b. So you have 2 values. We'll see how are we going to get that, but actually you have p of x is, right, the result of multiplying x to the j plus b, which are actually constants, j and b, they are numbers that you get. And then you have times a monic algorithm of degree, or 1 degree less than this one. The degree of this is 2 to the k minus 1. The degree of q and r is going to be 2 to the k minus 1 minus 1. So for example, if this is 2 to the 4 minus 1, 15, this is going to be 2 to the 3 minus 1, which is 7, right? So you have like 31, 15, 7, 3, 1, more or less, right? So that's the idea. So in fact, what you're doing here is you have this of size n, or 2 to the k minus 1. These are going to be 2 to the k minus 1 minus 1. And then you're going to solve this recursively, right? With polynomials that are, you know, 2 to the k minus 2 minus 1, and so on until you reach, you know, the limit condition there in the recursion. So let me just move on, right? So you need to evaluate, to evaluate px, you need to evaluate qx recursively, right? You need to calculate x to the j, and you need to calculate x to the j plus b by qx, and then add rx. So that's the operation that you do, basically. And what I want to show you, because q and r, right, the 2 algorithms, the 2 polynomials of, you know, 1 degree less than the p of x, have the same properties than p. They are all monotonic. The algorithm can be recursive. So this is a recursive algorithm. This is a divide and conquer algorithm for doing the solution of p of x, right? First, you choose j and b, right? J is a degree of p minus the degree of q, which is 2 to the k minus 1, minus 2 to the k minus 1 minus 1. which is 2 to the k minus 1. So that's the value of x to the j, I'm sorry, but and then the right value of b is obtained when we divide p of x by this, and we obtain q of x. So it's like, you know, you have a regular division in which you have p of x, and you have the expression here, x to the j plus b, right, which is a constant, and you are going to get the monic a polynomial q of x, right, of degree 2 to the k minus 1 minus 1, and the polynomial r of x, which is also the same degree as q, right? It's like a regular division, right? You have this number be divided by this, you are going to get this, and then you get the remainder here, right? And this is equal to this times this plus this, right? It's a regular division. So let me see what is next. Let me just jump the recursion. So this is the formal way of doing, you know, p of x here, x to the j minus plus b, x to the j plus b, and this is q of x, and this is r of x. And from here, you are going to get this harmonic algorithm, right? And b is this element in such a way that this minus this is going to give you 1 here, because this polynomial is going to be monic, and this polynomial is going to be monic also, right? So let me show you right? So this is x to the j plus b plus times q of x plus the residual, right? So this is the value of p of x, but you need to compute q of x again and r of x again, etc. So let me show you an example. I think you would understand better with the example. So you have the polynomial here, in which n is equal to 2 to the 3 minus 1, right? Which is 7. Okay? So you have this. And then you are going to start solving, right? K is equal to 3, right? And then you say j is equal to 2 to the 3 minus 1, which is 4, right? 2 to the 8, 2 to the 3 minus 1, which is 4 aquí. So you have j there. And then what you do, b is equal to 2 to the k minus 1, which is a to the 4, 3 plus 1 is 2, minus 1 is 3, right? A3 minus 1, right? Then b is going to be equal to 2 with this formula. So, and the formula is coming from the general expression here, right? This is b. So you compute that b also, right? So now you have a x to the j plus b is x to the 4 plus 2. So you're going to have this expression here. So you have the polynomial here, and then you have x to the 4 plus 2. So if you divide up this into this, right, you're going to get this, right? For example, x7. So you divide up first between this number. So x7 divided by x to the 4 is going to be x to the 3, you see? 6x to the 6 divided by the x4 is going to be 6x squared there. 5x to the 5 divided by the x4 is going to be 5x, right? And this divided by x to the 4 is going to be x, is going to be 4 only, right? And then you divide up by and then you say this expression 3x 3, so this is q of x, right? And this is so this time this time x4 is going to be x7, 6, 8, so this is going to be 0 here, and this multiplied by 2 is going to be 2x squared plus 12x squared, 10x, etc. So here you're going to get 0, and then the multiplication of this times this is this, and then you subtract, and here you get a monic, right? And then you subtract, and then you have r of x in such a way that this times this plus this is going to be expression here. Now, in order to solve the polynomial, you need to solve this and you need to solve this in the same way. So you are going to do the same for this same. So this is x to the 4 plus 2 times q of x plus r of x, right? But now you need to say, okay, I need to, q of x is this, I need to solve it again, right? And I compute, I have k, I have j, I have b, and then I get this expression, I get the new qx, and then I get the new r of x for this part, for q of x, and then I have for r of x the same array. I have k, I have j, I have b, right? And I solve, right? And so this is the solution for r of x, right? So q of x is going to be this, and r of x is going to be this. And the expression is this, the original, this is q of x, and this is r of x, right? And then for this case, what you need is, for example, you need 5 multiplications. So you have 1, 2, you have 3, and you have 4, x minus 20. 5 multiplications and 10 additions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'll find the multiplication. So I have, okay, so the multiplications is here, 1 is 1 here. So this is 2. This is 1. Oh, okay, so you need to find this times this is another one, is the 4th one, and this times this is the 5th one. So those are the 5 multiplications there in the 10 dimensions, okay, in addition. So this is, the analysis is evaluate Q of X and R of X. You compute X of J, which is, you use J this many times, 2 to the K minus 1. So you compute X squared, X to the 4, X to the 8, etc., X to the 2 to the K minus 1 by using K minus 1 multiplications, because you have X. And then X squared is 1, X to the 4 is 2, etc., up to here, right? Which is X to the 2 to the K minus 1. And compute this expression times Q of X plus R of X with 1 multiplication here and 2 additions, 1 here and 1 here. Let us do n to the k be the number of multiplication done to evaluate a monic polynomial of degree 2 to the k minus 1, and a to the k the number of addition and subtractions, then m of 1, which is in terms of k, right, is equal to 0. So if n is equal to 1, 2 to the k minus 1 minus 1 is equal to 0, right? So the number of multiplication is going to be 0 for that case. M to the k is going to be 2 to the mk minus 1, because you have two polynomials of size k minus 1 plus 1, right? Because you sum them up. And then for the additions is for the case in which you have a1 x plus a0, you have one sum here for a1, right? And then you have two subproblems of size k minus 1 plus 2, right? Which are two sums in it. Then you can solve these two expressions, m to the k, m of k and a of k, right? And then you're going to have this m of k is equal to n over 2 plus log n, which is a little bit better than linear, right? For the other algorithms, this is linear. And also for the fk, the number of additions is more or less 3.5 n, right? More or less, this is also linear, and this is also linear, a little bit less, than this number here, but here is difficult to improve a lot, right? Because they are very close, the algorithm. So this algorithm is also basically, we can say that it's linear, different perspective. The other two were iterative, and this is a recursive algorithm, right? For doing that. Okay, so questions about these algorithms for evaluating polynomials. So the best way to understand what it is the algorithm doing is, the example and try to understand what is happening there. But this is going to be one of the exact exercises in the homework. So question up to now. So this is, so classic method for multiplying two matrices and n to the cube, multiplications, n to the cube minus n square sums in the Strassen, and also we check the winograph, right? And there are three algorithms basically for evaluating polynomials. Okay, so far so good. What do you think? So let me just check the homework here. This is homework number 7. Let me check that here. Okay. There it is. So this is today's homework. And there are only 2 exercises here in this homework that it needs to be solved individually. So you have the first homework, which is individual, and this homework also individual, right? All the others are in couples. So what you're going to do is to generate, let me see if I can do something here. Okay. 2 exercises. One is an exercise in which you are going to generate 2 4x4 matrices in manually. So I hope this is the last time you're going to do this in your whole life, but you need to do it in order to understand the Strassen algorithm. So you're going to generate 2 matrices, right? 4x4, and then you're going to apply the Strassen algorithm to multiply them. Verify the result is correct by comparing with the one provided by the traditional method, right? Show the steps. So you're going to show all the steps in order to get the result of this multiplication of the 2 matrices using the Strassen algorithm, right? So what is going to happen is that you're going to generate x1 to x7 here, and in which you are going to have matrices of 2 times 2, right? And do the operations. And then when you reach to the point in which you are going to multiply 2 times 2 matrices, you're going to apply it again. And then you're going to get the result. And then you come back, right? Until you get the result of this multiplication, right? So this is what you're going to do. Try to generate the matrices with different numbers, avoid ones and zeros only, right? A regular, and then try to apply the traditional method, the conventional algorithm, and try to compare. So you're going to include all these steps in your solution, right? And in the other exercise, you're going to generate a polynomial, right? Which is monic. For k is equal to 4, so that is for n is equal to 15, and solve it using the recursive algorithm we just presented, right, in the lecture, right? So these are 2 exercises you're going to do in order to understand what is happening with the Strassen, in order to understand what is happening with this algorithm, the recursive algorithm for getting the evaluation of the polynomial, right? And then you try to generate this, and you generate the AIs also, right? And then try to solve, right? Questions so far? Is that okay? What do you think? So you have 3 homeworks now, 5, 6, and 7, and you should submit the solutions on the 22nd of April, right? I will upload a kind of announcement, right? A kind of reminder about these submissions that you have to do before the 22nd. Remember, Easter is from the 13th to the 20th, right, of April. And then after Easter, you're going to submit the homeworks, 5, 6, and 7. I will give you probably not the feedback, the direct feedback for those homeworks, but what we're going to do is to give you the solutions, right, in order to use them as a preparation for the exam, right? And the exam is going to be the 28th of April, right? So what I usually do is, let me see, because I think I have a trip on the week of the 22nd to the 25th. But I will try to give you a sample exam just for you to prepare for the real exam, right? In this exam, I usually include some exercises similar to the ones that you're going to find in the midterm. But I give you this sample exam at the end of that week, just previously before the exam, right? So I will, keep the schedule in all these announcements in order for you to be ready, right? The intention is that you are ready for the exam. But most important thing is that you solve the exercises in the homeworks, right? But this week, what I want to do on Friday morning is just to review the sessions 5, 6, and 7 in the homeworks. And if you have any questions and inquiries, please bring them with you so we can check them out in that session on Friday morning. Right? Questions? Is that clear?
Yes,
Yes.
it's clear.
Everything understood?
Yes.
Yes,
Yes.
thank you.
I have a question for the homeworks. If we're doing them in pairs, do we each upload the results or just one per team?
Is that okay? As long as you include the names in the cover page, that is okay, right? Or
Okay,
doesn't
thank you.
matter. But also, if you want to, upload it, just in case the others don't do it, it's okay also. So we actually try to revise as a team, right, and give you the mark. But at least one member of the team should upload the comment, right? But remember that this homework number 7 is individual, right? So all of you should upload the solution.
Yes.
Mhm. So, okay, so go on. You have, I know that you have a lot of topics to study, right? Introduction, algorithm, divide and conquer, dynamic programming, sorting, the different algorithms, selection, and also this matrix multiplication and polynomial evaluation. Some of the things I stress at some point in the sessions that you don't have to memorize things, but you have to understand what is happening, right? In order to tackle the exercises that you're going to have in the exam, right? So the exam is going to be online. Usually I put it there in about 15 minutes before we start at 4, and you can start, right? And you have until 7 that day to upload it. So you have to, you use paper, right, to write your exam. You don't use tablet or anything electronic to answer your exam. So you do it in paper, you scan it, and you upload it. That's the process, right? So you have to do it by hand. Is that okay? Is that clear?
Yes.
Yes.
Okay. And it's the same way that we are going to do with the final exam. So, okay, so up to today, these are the sessions for the midterm. Next week, I'm going to talk about graphs, graph algorithms, but this is just for the final, right? And then hyperheuristics, that is for the final project, basically, right? And then we just have additional sessions like parallel algorithms and then quantum computing. In that session in particular, Dr. Salvador Venegas, who is an expert on this topic, is going to give you an introduction. And it's important, you know, to have that basic knowledge on quantum, at least because it's an important topic that is going to develop in the future, I guess. Okay. Someone doing quantum computing in their thesis or someone? No? Well, you will meet Dr. Venegas anyhow. Okay, additional questions for this. Are we doing okay?
Yes.
Okay. So remember, any questions or issues that you may have, just send me an email. If you have the question there, I can just solve it, or if not, I can open up a session, a Zoom session, and we can discuss. Okay?
Doctor, Friday session is gonna be same time as always, 8:30?
8:30, yes. Mhm.
Okay,
Yes.
thank
Mhm.
you.
Okay, but I upload an announcement just to give you the details and everything, right? And a reminder. But it's going to be on Friday, 8:30. Okay?
Thank you.
All right. Okay. Thank you very much, and take care. And I'll see you soon.
Bye.
Thank you,
Thank you,
Professor.
Professor.
See you.
Okay.
you.
Thank
Bye.
you.
Thank
Thank
you.
you.
Bye-bye.
Thanks, Professor.